All right, calculus class, here we go. We're taping another video. It's Wednesday. All right, we left off in class on whatever day it was, Monday or Tuesday, talking about the concavity of curves, and we concluded that the second derivative tells us, the sign of the second derivative tells us whether the function is concave up or concave down. And using this, we can sketch a lot of curves. So let's do some more of these because they get kind of complicated. So here we go. Here is a function, not so bad, it's a polynomial. F of x equals x to the fourth minus 4x cubed. And in fact, you probably kind of know something a little bit about what this function looks like already. So all right, let's do it. We take the, oh, and for all of the problems that we're going to do right now, please get out a piece of paper, get out a pencil, and try them all yourself first. I'm going to go fast, pause, do the entire problem, and then look and see what I did. You have to try it yourself. Don't just watch. Okay, so here is the procedure. We take the derivative. So I get 4x cubed minus 12x squared. And so, yeah, there it is. All right, let's factor the derivative. So I can factor a 4x squared out of both of these, and I'm left with x minus 3. Okay, looking good. Now, while I'm at it, I am going to take the second derivative. So the second derivative is 12x squared minus 24x. So then I can factor that. So I can take a 12x out of both, and I'm left with x minus 2. Okay, beautiful. Let's now make our picture. Yeah, first of all, this is kind of an optional first step. Let's look at when the function is positive and when the function is negative. And of course, this function can be written as x cubed x minus 4, which tells me that if this is 0 and this is 4 over here, that the function will be, let's see, there's a sign change at 0, it's quartic, end behavior like this, and therefore it is positive, negative, positive. Okay, so that's good to know. Let's look at the sign of the derivative. The derivative is 0 at 0 and 3. So here's 0, here's 3. But there's no sign change at 0. So in fact, you maybe could have left that off entirely, the number line. The only sign change is at 3, so it must go negative, positive. So it's going to be negative, negative, positive, which means my function is decreasing, it's still decreasing, and now it's increasing. The second derivative, number line, looks like this. It's gonna, there's a 0 at 0, and there's another one at 2. Quadratic, end behavior positive, so plus, minus, plus, which means it's concave up, concave down, concave up. And now I superimpose these, the f prime and the f double prime number line. Some interesting things happen at 0, at 2, and at 3. On the interval negative infinity to 0, it's decreasing concave up, so that's like that. On the interval from 0 to 2, it's decreasing concave down, so that's like that. From 2 to 3, it's decreasing concave up, so like that. And from 3 to infinity, it's increasing concave up. Okay, so yeah, looking good. So I now know everything I need to know to graph this. Let's get some points. Of course, f of 0 is 0. f of, I guess 2 and 3 are important, so f of 2 is, it's best to plug it in here, I guess, 8 times negative 2, so that's negative 16, and f of 3 is 27 times negative 1, so negative 27. Alright, so if I want, I can now make a very accurate graph of this function. At 0, 0. At 4, it's also 0. At 2, it's negative 16. So I'll just 2, negative 16. And at 3, it's negative 27. So I'll just do that. 3, negative 27. Okay, what is this function doing? Well, it's decreasing concave up on the interval from 0, negative infinity to 0. At 0, we have a point of inflection. So here, not only is the function 0, not only is the derivative 0, which means it's a horizontal tangent line, but also the concavity changes there, and we get one of those kind of cubic-y things, which I sort of knew about already. What else do I know? I know that there's a relative min at 3, so it's doing a little bit of that. And at 2 is another concavity. It's the place where the function changes from being concave down to concave up. So we have something like this. And while this is largely, this is sort of things that we already knew just from like pre-calc. We kind of knew that this function looked like this. We knew that its end behavior was like this. We knew there were roots at 0 and roots at 4. We knew that it was kind of cubic-y at 0. Now, with calculus, I can tell you that I can calculate exactly where the relative min is. It's here. And I can calculate exactly where the point of inflection is. And this is also a point of inflection. Okay, cool. Another thing. So let's see. I'm gonna move this. Yeah. Okay. Let's take a function now. Watch this. Take a function x to the 5th minus 5x plus 3. Okay, so changing the subject for a moment. Suppose now I don't want to get a graph of the function. I just want to find the extrema. So goal, find the extrema, the relative extrema. Okay. How can I do this? Well, the old way was that you take the derivative. So you get 5x to the 4th minus 5, factor out the 5, x to the 4th minus 1, and then this is 5, x squared minus 1, x squared plus 1, and I could even write it as 5, x squared plus 1, x minus 1, x plus 1. Which means that the derivative looks like this. Try this. Oh, again, please, as soon as I put a new problem on the board, please hit pause, do the entire problem, and then like fast forward a couple minutes and see what I'm talking about. So that means that's always positive, so I can ignore it. So this root's at -1 and 1. It's quadratic-y, so it's positive, negative, positive. And then the first derivative test tells us that there's a relative min here. And suppose our goal is not just to find out where there's a relative min, but to justify the existence of the relative min. Well, I can, of course, use the magic sentence, and I can say, or sorry, this is a relative max. So I can say f has a, well, let's do it properly. F prime changes sign from positive to negative at x equals -1. So f has a relative max at x equals -1. Okay, and all of that is fine. But let's suppose now that I also wanted to take the second derivative, because maybe I want to know where the concavity changes or whatever. So let's do that. Take the second derivative of this function. And because it's a polynomial, taking the second derivative is really easy. It's just 20x cubed. Yeah. And of course, there's only one place where the second derivative is 0. So if I make my f double prime number line, then this is going to be negative and then positive. Which means it's concave down, and then it's concave up. Okay. What is going on at -1? If I kind of think about this for a minute, I notice that -1 falls in this region. In other words, f is concave down at -1. And so I have a situation in which I have a function in which at -1, I know that the, what happens if I plug -1 in here? I get 8 minus 1, I get a 7. So, right? -1, and yeah. So at -1, this function is 7. But now I know two things about this function at -1. I know, because the derivative is 0, that there is a horizontal tangent. So I'm going to draw in a little horizontal tangent line. But I also know that this function is concave down. And the definition of a function being concave down, hands on the elephant, that the tangent lines lie above the curve. So that there is a horizontal tangent at x equals -1 because the derivative is 0, and the horizontal tangent line lies below the curve. So the only possibility is that the function looks like this. So I know that this function must have a relative max at x equals -1 because of the sign of the second derivative. And this is something which is called the second derivative test. Yeah, second derivative test. And the second derivative test is, this is a method for justifying the existence of relative extrema. So it's an alternative method. It's an alternative method for discovering slash justifying the existence of relative extrema. In other words, you use the first derivative test or you use the second derivative test. You wouldn't use both. And the second derivative test has nothing to do with concavity or points of inflection or anything like that. It is a method for justifying extrema. And here's what the second derivative test says. It's quite obvious, or it's quite intuitive. The second derivative test says, well, suppose f prime at some point A is 0, and f double prime at A is positive. Well, what do I know about the function there? If I make a picture, at A, I know my derivative is 0. It's just repeating the exact same thing we said. I know my derivative is 0, which means, let's suppose that when I plug it in, I get this value here. So that's f of A. Since the derivative is 0, it means there's a horizontal tangent. But since the second derivative is positive, it means it's concave up. And if it's concave up, all tangent lines must lie below the curve. So if all tangent lines must lie below the curve, then by the definition of relative minimum, this is a relative minimum. Because for any number nearby, if this is a horizontal tangent and the horizontal tangent lies below the curve, then the function lies above this horizontal tangent line. In other words, all the y values of the function are greater than this y value. But this y value is the y value at A. So the conclusion is f has a relative min at x equals A. And the other way to do this is if you have different information, if you have that f prime of A is 0 and f double prime of A is negative, then you have the situation we were just talking about before. So here's A, here's f of A. I know the derivative is positive, so that my derivative is 0, so I have a horizontal tangent. And the second derivative is negative, which means concave down. Tangent lines lie below, the tangent lines lie above the curve. The function lies below its tangent line. Conclusion, f has a relative max at x equals A. And so if you want to see the second derivative in action, we can apply it to this particular problem. So again, you could do this, or you could say, looking back at this function from a few minutes ago, your alternative technique is to say f prime of -1 is 0 and f double prime of -1. Well, now just plug -1 into f double prime. It's -20, which is negative. So by the second derivative test, the derivative is 0, but the function's concave down, then there's a relative max. F has a relative max at x equals -1. Okay, so the second derivative test, some people love it, other people don't. You don't ever have to use the second derivative test. It's just a good option when if you don't feel like writing the magic sentence, or you don't feel like figuring out where the first derivative is positive or negative. And the thing about the second derivative is, there are basically two kinds of functions. There are functions which get easier the more you differentiate them, like polynomials, and there's functions which get more complicated the more you differentiate them. So, I don't know, I think we should maybe let's do one more quick example of this. Let's do one more quick example of this. So let's take the function x e to the x, and let's find the relative extrema using the second derivative test. Second derivative test. Okay, so here is the function. F of x equals, f of x is x e to the x. Okay, please, pause. Do it yourself. Take the first derivative factor, take the second derivative factor, make the chart, do the whole thing, then watch. I'm going to go really fast. So pause it now. So take the derivative first. Yeah. First times the second. First. So that was pretty easy. And the derivative is then e to the x plus 1. I feel like I did this problem already. Yeah. I think I did this problem with my other class. And then take the second derivative. Well, the second derivative would be e to the x plus, the derivative of that is just another e to the x plus x e to the x. And so the second derivative is 2e to the x plus x e to the x. Or it could be factored as e to the x times x plus 2. Okay, so I can make my sign chart for f prime. Actually, let's just graph this whole thing. I think we should do that. So let's make my sign chart for f prime. Is this thing okay? Yeah. So we're going to graph this whole thing. So make my sign chart for f prime. I did this problem, I realize now, in fourth period only. So if you're in fourth period, we did this already. The other periods, keep watching. So I took all my derivatives nicely factored, and let's make the sign chart for f prime. Well, that's always positive, so only that matters. So we'll look at -1, and it's going to go negative, positive, which means the function's decreasing, then increasing. Okay, let's make the sign chart for the second derivative. The second derivative changes sign at -2. So we get one sign change, and it goes again from negative to positive, which means it's concave down and then concave up. So now we make the sign, now we put it all together, so that's -2, -1, and we see that the function's decreasing concave down, so like that. Between -2 and -1, it's decreasing concave up, so it's like that. And then from here, on this interval from 1 to infinity, it's increasing concave up. And the one other thing, we talked about this in fourth period, sometimes it's helpful to make a sign chart for f. We did this a few minutes ago. So f is going to be negative and then positive. Okay, so this is a great function that you would have had no chance of being able to graph in pre-calc, but with calculus, every single facet of this function is revealed, all of this information. So then, let's make a graph of it. Let's get some numbers. So f of 0 is 0. F of -1 is negative e to the -1. E to the -1 is 1 over e, so it's -1 over e. So that's approximately, it's like approximately -1/3, let's say. And then f of -2, if I plug -2 in, I get -2 times e to the -2. E squared is about 7, so e to the -2 is like 1/7. So this ends up being like, what did I say? -2 over e squared, which is approximately -2/7. So, if I'm going to make a graph of that, what is this going to look like? Well, here it's 0. Let's see. -1, -2, and here's -1. So when I plug in -1, I get like -1/3. So this is my point, -1, -1 over e. And which is bigger, -1/3 or -2/7? It's pretty close, but this number is closer to 0. Also, I know that the function is decreasing here. So a little bit up here, I have my point, -2, -1 over e squared. And also, I think also that the end behavior is important. So what is the limit as x goes to infinity of x e to the x? Well, clearly that's infinity. What's the limit as x goes to -infinity of x e to the x? Okay, this is a little bit less obvious because as x goes to -infinity, that's like a huge number, but that is like a really, really tiny number. But if you kind of think about it, let's just think like -1,000,000. So if you think like -1,000,000, what is this? This is like negative 1,000,000 in the numerator. Okay, that's definitely big. But e to the negative 1,000,000 is like 1 over e to the million. And that is definitely going to 0. So this is like 0. It's like a 0 minus even. You're going to do something in analysis 1b, which enables us to calculate that kind of stuff more exactly. So what we have is the following situation. There is a relative min at -1. So I'll draw in this little relative min. And there is a point of inflection at -2, is where it changes from being concave down to concave up. And this guy also has an asymptote of y equals 0. So this curve is going to come. It's concave down. Concavity changes at -2, and now it stays concave up forever. It's going to look something like that. Pretty awesome function, actually. So right here is a point of inflection. That's what my chart says. And right here is a relative min. Okay. Time does it say? Yeah, so then if they wanted me to also justify this, I could do it in 2 ways. Let's do it the second derivative test way, because we're practicing that. The second derivative test, if you want to justify the relative min here at -1, you would say f prime of -1 is 0, and f double prime of -1, and you plug now -1 into f double prime, and you get 1 over e times 1. So you just get 1 over e. And that number is positive. And since there's a horizontal tangent line and the second derivative is positive, it means it's concave up. So it's a relative min. So f has a relative min at x equals -1. So by the second derivative test. By the second derivative test. Some people like that better than the first derivative test. Okay, plan for now. We are going to graph. We're going to graph 3 functions and using this technique, and then that's it. I think I'm going to pause this. Yeah, I'm going to pause this.